In our previous video, we have introduced the molecular orbital theory as the most general type of theory to describe bonding in chemistry. And while it is the most general, it is also the most abstract, and therefore it may take a while for you to get used to the shapes and the concepts that molecular orbital theory brings in. On this slide, you can see the molecular orbital diagram of the simplest molecule, which is the dihydrogen molecule. The dihydrogen molecule has this scheme of molecular orbitals. What is this? Well, if you approach, say that this is the 1s and this is the other 1s, and you approach them, because the actual 1s is more of a wave, you can the waves can interact in two main ways. If they interact in a constructive way, they will give what we call the bonding. This is the bonding interaction, the bonding interference. Or if the waves, one is like this and the other one is like that, they will give a non-bonding interaction, this being hydrogens. Okay, hopefully you get a little bit the idea. As you get them closer, there exist two possible combinations of atomic orbitals: the bonding molecular orbital and the anti-bonding molecular orbital. So one first comes up with the overall scheme. Now we know that when we mix two atomic orbitals, we come up with two possible molecular orbitals, and because each of the atomic orbital brought one electron, we need to place now two electrons in here, and we will start using the same Aufbau principle we use for atoms, and we start from the most stable, the lowest energy orbital, and going up, following, of course, Pauli's exclusion principle, that you cannot put more than two electrons and they have to be with opposite spins. So this is why the electronic configuration of the molecular H2 is 1s2, and if you will, in the 1s antibonding there is 0 electrons. Okay, so what kind of questions can you answer about this? You can ask about the bond order of this molecule, identify the HOMO and LUMO, that we will just talk about what this is, and explain why is it that these molecular orbitals are called sigma. Okay, and finally what we did here is write the electronic configuration. So let's try to see how we can calculate the bond order for this molecule. Well, the bond order is calculated by adding the electrons in bonding orbitals, subtracting from the electrons in anti-bonding molecular orbitals, and divided by 2. So in our case, the bond order for hydrogen, if you look, we had 2 electrons in the bonding, 0 in the anti-bonding. Therefore, I have 2 minus 0 divided by 2. No surprise, the bond order is 1. Notice that this was we could already have predicted bond order of 1 using Lewis structures, so that's not an example where molecular orbital theory shows its power. Another concept that we were just asked about is identify the HOMO and the LUMO. The HOMO is these are the acronyms for the highest occupied molecular orbital. So the highest occupied molecular orbital, this one is the highest occupied molecular orbital. There's actually only one occupied, so this is our HOMO. And the LUMO is the lowest unoccupied molecular orbital. This is where the LUMO is. You will see that the concept of HOMO and LUMO is a very useful one, because that's where chemistry takes place. When electrons, if you will, combine between HOMO and LUMO, that's where chemistry will give its results. So you will see this because in large molecules there's actually more than 2 molecular orbitals, so the energy and the shape that the HOMO and the LUMO have will be able to describe a lot of the chemistry of that specific molecule. So keep these two concepts in mind. And finally, the nomenclature that we already mentioned. If the molecular orbital has density along the axis of the molecule, we call that molecular orbital sigma, which is the Greek letter for S. And if the molecular orbital has density outside of the axis of the molecule, we call that a pi bond, okay, which is the Greek letter for P. All right, so just making sure, identify the home on the LUMO. We did that. Is the bonding in the axis out of the axis for the molecule? Is it sigma? Is actually, it's not outside of the axis. Notice that the bonding takes place between the atoms, therefore it's a sigma molecular orbital. Okay. And something else that we already have described is we are going to use the same concepts for electronic configuration. The most stable electronic configuration is when you place all of the electrons in the lowest energy molecular orbitals, provided that you do not violate Pauli's principle. So in this sense, this electronic configuration, the one that you see here, in which two electrons are in the bonding, has a lower energy, therefore it's more stable than if you promote one of these electrons up here. So this, the molecular orbital diagram that you see on the right, has a higher energy and therefore less stable. One can go from here to here, usually with a laser or with some light, and if you put too much light, you may even ionize the electron, or the molecule I should say. And again, this is not the case, but if we had pi bonds, so in the case that there would be degeneracy between the molecular orbitals, we follow Hund's rule, in which the electrons being in parallel spins in separate orbitals will have a stronger stability, lower energy than if they are in the same electron. In the same molecular orbital. These are the same rules applied to atomic orbitals, so they should not be that new.